Previous class we discussed about the closed pack structures, that is closed packing in the 1 dimension and 2 dimension 3 dimension we are discussed in the previous class. In this class we are going to be discussing about the voids in crystalline solids. The voids are also be called as a holes or interstices. What is meant by voids? The empty space present between the spheres. The spheres is nothing but the particles in a closed packed structure are called voids. Means the empty space present between the spheres in a closed packed structure are called as a voids or holes or interstices. Then now these voids are, there are three types of voids. That is, one is triagonal void. The second one we called as a tetrahedral void. Then octahedral void. There is a we'll discuss one by one. The first one we will discuss about the triagonal void. The triagonal void means the void between the three spheres touching each other. Means if it is having the three spheres, the void between the three spheres, this empty space is there, no? This we called as a triagonal void. This we call as a triagonal void. Means here the space between the empty space between the three spheres touching each other, that we called as a triagonal void anta kariತೀವಿ. Then the next we are going to be discussing about the tetrahedral void. These in HCP and CCP, the void surrounded by four spheres. That is, three in the same plane and one in the second layer are called tetrahedral void. How means it's going to be the three spheres. It's going to be touching each other. Three spheres is going to be touching each other. These three is present in the same layer. Another sphere is present in the above that layer is called this void we called as a tetrahedral void. This we called as a tetrahedral void. Means the void in between the four spheres. That's why it's called as a tetrahedral void. Then the next one we will discuss about the octahedral void. The void surrounded by the six spheres. Means if suppose if you are going to be taken that three in the same plane, the three spheres in the same plane, another three spheres in the another plane. This void we called as a octahedral void. Means the void surrounded by the six spheres, which centers of these six spheres are joined, and an octahedron is formed. Hence the void is called as a octahedral void. The centers of these spheres is joined, we are going to get the tetrahedron. That's why it's called as a tetrahedral void. If it is joined, the centers of these will get that octahedron. That's why it's called as a octahedral void. Now we are going to be discussing about the location. That is the location of voids in a crystals. Location of voids in crystal. When it comes to that location of voids in crystal, the closed pack structure, that is CCP or FCC, that is if there are n spheres in the packing, then number of octahedral voids and the octahedral voids is going to be octahedral voids is n, then tetrahedral wires is 2n. We are going to be, means the n where n is nothing but spheres, number of spheres. N is nothing but n number of spheres. Suppose if you are going to be taken example cubic close packing, that is CCP. If you are going to be taken the CCP, cubic close packing, the number of atoms in that is 4. We are going to be taken the 4 atoms is going to be present in that. Means here the octahedral voids is equal to, we are going to be taken that 4 only, that then tetrahedral voids we are going to be taken that 4 into 2, that is we are going to be get that 8 tetrahedral voids per unit cell in the CCP. Means per unit cell the 4 atoms present in the CCP, therefore octahedral voids we are going to be taken, that is n is nothing but 4. ಎಷ್ಟು ಸ್ಪಿಯರ್ಸ್ ಇರುತ್ತೆ ಅಷ್ಟೇ ನಂಬರ್ ಆಫ್ ಆಕ್ಟಾಹೆಡ್ರಲ್ ವೈಡ್ಸು ಕೂಡ ಇರುತ್ತೆ. ಅದೇ ಥರ ಟೆಟ್ರಾಹೆಡ್ರಲ್ ವೈಡ್ಸ್ ಏನಾಗುತ್ತೆ, ಡಬಲ್ ಆಗುತ್ತೆ. ಇಟ್ಸ್ ಗೋಯಿಂಗ್ ಟು ಬಿ 2n, ದಟ್ಸ್ ವೈ 2 into 4, ದಟ್ ಈಸ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಬಿ ಗೆಟ್ ದಟ್ 8 tetrahedral voids. Like that only if you are going to be taken that the hexagonal close packing, HCP, if you are going to be taken that HCP, hexagonal close packing, there are 6 atoms or ions for unit cell, 6 octahedral voids, and that is octahedral voids is going to be 6. Then tetrahedral voids is going to be, we are going to be taken that 6 into 2, that is 12 per unit cell. This about the location of voids. Location of voids in a crystal, we are going to be taken that n is the number of spheres, octahedral voids is going to be n, tetrahedral voids is we are going to be taken as the 2n. Like this we can calculate the number of total octahedral voids and the tetrahedral voids present in the crystal. Now we are going to be discussing about the next topic that we call as the packing efficiency. What is meant by packing efficiency? That is packing efficiency. That is packing, if we arrange the particles in different form, it is not possible to occupy the entire availables. ಹೆಂಗೆ ನಾವು ಅರೇಂಜ್ ಮಾಡಿದ್ರು ಪಾರ್ಟಿಕಲ್ಸ್ನ ಒಂದು ಕೊಟ್ಟಿರೋ ಸ್ಪೇಸಲ್ಲಿ ಹೆಂಗೆ ಅರೇಂಜ್ ಮಾಡಿದ್ರು, ನಂಬರ್ ಆಫ್ ವೇಸ್ ವಿ ಕ್ಯಾನ್ ಬಿ ಅರೇಂಜ್ ದ ಪಾರ್ಟಿಕಲ್ಸ್, ಬಟ್ ಎಂಟೈರ್ ಅವೈಲೇಬಲ್ ಸ್ಪೇಸ್ನ ಆಕ್ಯುಪೈ ಮಾಡೋಕ್ಕೆ ಸಾಧ್ಯನೇ ಇಲ್ಲ. ದೆರ್ ಈಸ್ ಆಲ್ವೇಸ್ ಸಮ್ ಫ್ರೀ ಸ್ಪೇಸ್ ಇನ್ ದ ಫಾರ್ಮ್ ಆಫ್ ವೈಡ್ಸ್. ಸ್ವಲ್ಪ ಜಾಗ ಉಳಿದೇ ಇರುತ್ತೆ. ಅದನ್ನು ನಾವು ಎಷ್ಟು ಪ್ಯಾಕಿಂಗ್ ಎಫಿಷಿಯನ್ಸಿ ಅಂದರೆ, ದಟ್ ಈಸ್ ಪ್ಯಾಕಿಂಗ್ ಎಫಿಷಿಯನ್ಸಿ ವಿ ಕ್ಯಾನ್ ಬಿ ಡಿಫೈನ್ಡ್ ಆ್ಯಸ್ ದ percentage of total space occupied by the particle in a crystal is called packing efficiency. The packing efficiency formula we can be written as the packing efficiency is equal to, that is the volume occupied by the sphere in unit cell divided by, that is total volume of that is total volume of unit cell into 100. This is the formula used to calculate the packing efficiency in SCC, BCC, FCC, like this different unit cells. We can be calculate the packing efficiency of different unit cells. Now we are going to be discussing about the how to calculate the packing efficiency in SCC. That is simple. This is a very important question for the examination sake. Compulsory, 100% compulsory question. Then in that how to calculate means, in simple cubic lattice, atoms are located only on the corners of the cube and the particles touch each other along the edge. Means the ಒಂದು ಸಿಂಪಲ್ ಕ್ಯೂಬಿಕ್ ಯೂನಿಟ್ಸ್ ಎಲ್ಲ ತಗೊಂಡ್ರೆ ಕಾರ್ನರ್ಸಲ್ಲಿ ಮಾತ್ರ ಪಾರ್ಟಿಕಲ್ಸ್ ಪ್ರೆಸೆಂಟ್ ಇರುತ್ತೆ. ಯು ಕ್ಯಾನ್ ಅಬ್ಸರ್ವ್ ದಟ್ ಈಸ್ 8 particles is present at the corners of the unit cell. That is this length we are going to be taken as, the edge length we are going to be taken as A, small a. That we are going to be naming this unit cell, that is A, B, C, D, E, F, G, H. Let the edge length of the cube, ಇಲ್ಲೇನಂತ ತಗೊಂಡಿದ್ದೀವಿ, ಎ ಅಂತ ತಗೊಂಡಿದ್ದೀವಿ. ಲೆಟ್ ಎಡ್ಜ್ ಲೆಂತ್ ಆಫ್ ದ ಕ್ಯೂಬ್ is equal to A. Then radius of each atom, this radius we can be called as radius, that is R. This when we call as R, that is radius of each atom. Radius of each atom is equal to R. Radius of each atom is, thus we can be taken as these two are related as, ಇವಾಗ ಎ ಅಂತ ತಗೊಂಡ್ರೆ ಎಡ್ಜ್ ಲೆಂತ್, ದೆನ್ ಎಡ್ಜ್ ಲೆಂತ್ ವಿ ಕ್ಯಾನ್ ಬಿ ಟೇಕನ್ ಆಸ್ 2R ಅಂತ ತಗೋಬೋದು. Then we can be written as A is equal to 2R. This 2 we can be related like this. Then the volume of the cubic unit cell is equal to A cube. A is nothing but 2R whole cube. Then we can be written as 8R cube. Then the volume of the cubic unit cell, we got the 8A cube. We know that since already we calculate number of particles in SCC, that is a simple cubic unit cell is equal contains 8 into 1 by 8, that is 1 particle is present. The volume of the one atom or one sphere. Atom is nothing but in the form of sphere, that we are going to be taken. One sphere is equal to 4 by 3 pi r cube. The volume of the circle we are going to be taking 4 by 3 pi r cube formula use ಮಾಡ್ತೀವಲ್ಲ ಅದನ್ನೇ ಇಲ್ಲಿ ಯೂಸ್ ಮಾಡಿ. Then the packing efficiency is equal to volume of one sphere or one atom, or ಇದು ಆಟಮ್ನ ಸ್ಪಿಯರ್ ಅಂತಲೂ ಕೂಡ ಕರಿಬೋದು. ವಾಲ್ಯೂಮ್ ಆಫ್ ಒನ್ ಸ್ಪಿಯರ್ ಡಿವೈಡ್ ಬೈ ಟೋಟಲ್ ವಾಲ್ಯೂಮ್ ಆಫ್ ದ ಯೂನಿಟ್ ಸೆಲ್ into 100. Then now we are going to be taken as 4 by 3 pi r cube divided by 8 r cube into 100. That is r cube gets cancelled. Then after calculating this, that is a 4 4 pi 4 pi divided by 24 into 100. Then 4 ones are 6. That we are going to be get that pi by 6 into 100. By taking the pi value, we are going to be get that calculating. We are going to be get that 52.4%. That is pi value 22 by 7. If you are going to be taken this calculating, we are going to be get that is 52.4%. This is the way to calculate the packing efficiency in the simple cubic unit cell. Once again I will explain. The packing efficiency means the percentage of total space occupied by the particle in a crystal is called as the packing efficiency. The formula used to calculate the packing efficiency is equal to volume occupied by the sphere in a unit cell divided by total volume of the unit cell into 100. Then edge length of the cube is equal to, we are going to be taken as A. Edge length of the cube we are going to taken as A. Radius of each atom we are going to be taken as R. These two are related. If the edge length taken A, then this also be radius of these two atoms, that is going to be 2R. A is equal to 2R. The volume of the cubic unit cell is equal to A cube. A is nothing but 2R, that we are going to be taken as 2R whole cube, that is 8 cube. We know that number of particles we are already calculated. That is a simple cubic unit cell contains the 8 particles at the corner. It's going to be shared by 1 by 8 to the each unit cell. Then is equal to, we are going to be get that 1. Then the volume of one atom or sphere is equal to 4 by 3 pi r cube. Then the packing efficiency is equal to formula volume of one sphere divided by, if in this SEC we are going to be taken that 1. In other that is unit cells, we are going to be, it's very different. Then total volume of the unit cell is into 100. That is 4 by 3 pi r cube by 8 r cube into 100. That is going to be, now simplifying this, we will get that 52.4%. This is about the packing efficiency in the SEC. Then the vacant space available in the simple cube means, if you are going to be taken that vacant space, then vacant space ಎಷ್ಟಿರುತ್ತೆ, 52.4% ಅಷ್ಟು ಪ್ಯಾಕಿಂಗ್ ಆಗಿದೆ, ಸ್ಪಿಯರ್ಸಿಂದ ಫಿಲ್ ಆಗಿದೆ. ದೆನ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಬಿ 100% ಇನ್ SEC. We can be taken as, that is 100 minus 52.4. We are going to be get that 47.6. This about the vacant space in SEC.